Hello friends, welcome to YouTube channel SN Physics. In my previous video, I have discussed about the hybrid parameters and also discussed how to draw AC equivalent circuit using these hybrid parameters. Watch this video first and then it will be very helpful to understand this video on simplified hybrid model. Okay. For a large swing of base currents IB, as happens in power amplifiers, the collector current IC can be expressed as a power series IC equal to some constant plus some constant into base current plus some constant into base current square, that is higher orders of the base current. This is the actual relation between collector current and the base current. Small letters indicates AC signal. But for small signals, IB being small, its square Q can be neglected. And neglecting the higher terms, we are left with IC is equal to A0 plus A1 IB, which is a linear relation. Y is equal to Mx plus C. It is a linear relation. So, hybrid model is a linear approximation, which I have discussed in my previous video also. Now, in the previous video, the model was accurate and in details we can find out all the amplification factors, current gain, voltage gain, etc. very accurately. But in most practical cases, instead of making lengthy accurate calculations by using the complete hybrid model, we can use a simplified hybrid model that will help us in analyzing the circuits in a very simple manner. Calculations are very easy. Not only that, the result is almost same as the result obtained from the complete hybrid model. They are completely in agreement with each other. This is because by making exact analysis, one can get exact answers provided H parameters are known exactly. But H parameters are not accurate enough, as because H parameters vary widely for the same type of transistor. Say for CL100, it can vary from 100 to 400. For the same transistor CL100, which is an NPN transistor, its HFE varies between 100 to 400. We have taken typical value here as HFE is equal to 200, the average of 100 and 500. So, as because HFE is not so accurate enough or fixed for a particular transistor, we can approximate a model which is called simplified hybrid model. Not only HFE, it is true for HIE, HRE, HOE, all parameters. The simpler approximation solution may provide a better understanding of the physical process undergoing in the circuit, and the ultimate result does not vary much with the accurate one with the complete hybrid model. So, here HRE, its typical value is of the order of 10 to the power minus 4. It is very small. So, HRE into VO, it tends to 0, can be neglected. Another approximation, HOE, is of the order of 10 to the power minus 5 ampere per volt. So, its impedance 1 by HV is large enough. This impedance is in parallel with the load resistance. So effectively 1 by R is 0 plus 1 by RL, that's equal to 1 by R equivalent, as because this impedance and RL are in parallel. So R equivalent is equal to RL. We can neglect the effect of HV. So HV can be neglected in comparison to load RL in parallel. With all these approximations, the circuit is very simple now. The actual complete hybrid model circuit, as equivalent circuit, was there is a HRE here. Now we have assumed HRE tends to 0. In practical cases, this is very small, so it can be short circuited very easily. So if we short circuit these 2 points, HIE and VI are there. So this is HIE and VI. So between base and emitter only HIE exists, which gives input voltage. As IB is the base current, so input voltage is IB into HIE. VS is the AC source and its resistance is RS. Secondly, I have told you HV can be neglected as it is parallel with RL. So in complete hybrid model, 1 by HV is in parallel with RL. If we neglect this, we are left with this current HIE IB. So our equivalent circuit is HFE IB with RL in this position. Note that IO, output current, conventionally in this direction, inward, but in actual circuit load current flows out of collector point through RL. So IL load current IL, which is actually minus IO. These two currents are not different two currents. IL is nothing but minus IO. It is very important, note this point. Output is IL RL, output voltage. Now current gain is output current divided by input current. Our output current is IL, load current in reality, and base current is the input current. So IO is nothing but HFE IB. So IO being minus IL, therefore it is minus HFE IB, and IB is here, so it is simply minus HFE. So it is forward current gain with in common emitter mode is current amplification factor of the transistor in simplified hybrid model. Similarly, input impedance is nothing but input voltage divided by input current. Input voltage VI is HIE, the impedance, and current. So input voltage is HIE IB divided by IB, that is HIE. Similarly, voltage gain is output voltage divided by input voltage. Output voltage is ILRL, but IL is minus IO. Now ILRL divided by input voltage is nothing but IB into HIE. IB is input current. It may be written as II is equal to IB. So it is here ILRL, output voltage, and input voltage is IIZI. Now II is nothing but IB, so it is IL by IB, and it is RL by ZI. IL by IB, we have already told you this is current gain. So we can write this as IAI, and this is RL by ZI. Putting the value of AI, which is minus HFE, so it is minus HFE RL, and ZI is just HIE is HIE. So voltage gain is minus HFE RL divided by HIE. It's a very simple relation. It is easy to memorize and is very important. Note that in complete hybrid model, if we analyze the circuit with this circuit, current gain is minus HFE divided by 1 plus HOERL. But HOERL being very small, it is simply minus HFE, which is the result as we shown in this form. Again, voltage gain in the complete hybrid model can be shown as this, where delta H is HIE HOE minus HOFE HRD. If you put the practical values of all these parameters, delta H is very small, so this can be neglected. So it is left with minus HFE RL by HIE, which is nothing but the result minus HFE RL by HIE. So if we use the practical values, then this simplified hybrid model gives almost accurate results in comparison to results obtained from the complete hybrid model. But these calculations are complex enough, but these calculations are very simple. So this is the utility of the simplified hybrid model. Note that in this circuit, emitter is grounded. There is no resistance between emitter and ground. This is the emitter point, this is the base point, this is the collector point. Here is also, this is the emitter point, grounded, this is emitter, all those are connected to ground. This is the collector point, this is the base point. So in between base and emitter, there is a impedance HIE. Between collector and emitter, there is a current source HFE IB. So this is the important point in the simplified hybrid model. We can find out output impedance also, which is nothing but V output by I output. I output is HFE input current, which is 0, as because in calculating output impedance, it is obtained setting Vs equal to 0 and RL equal to infinity by definition. So output impedance becomes infinite. Here output impedance tends to infinity because it can be found setting Vs is equal to 0 and RL is equal to infinite open circuit. Driving output terminals by generator VO. So as RL tends to infinity, I output tends to 0 as it is open circuited. So output impedance, which is VO by IO being 0, it tends to infinity. Now we will analyze an important circuit, which is CE amplifier with emitter resistance. CE amplifier with emitter resistance. Why we are interested about the emitter resistance? Why we are connecting emitter resistance? Note that in this circuit there is no emitter resistance, but now we are connecting a resistance in the emitter called emitter resistance, and to bypass the AC component, we are connecting a capacitance parallel to RE, say CE, which is called bypass capacitor, which bypasses the AC component, so that DC biasing remains in the desired region. I will discuss the functions of input capacitance, output capacitance, CE, all this in my next video on RC coupled amplifier in details. Here we will discuss the importance of RE. Transistor parameters depend on temperature, aging and operating point. Operating point means whether it is in active region or in saturation region or in cutoff. Moreover, these parameters vary widely even for transistors of same type. If it is CL100 or CK100, the parameters are different for different transistors with the same model CL100, same model CK100. CK100 is PNP and CL100 is NPN. Or BC107, its parameter values vary with temperature, aging and for manufacturing problems. As a result, the voltage gain may become unstable. The problem is more severe in a multi-stage amplifier. Thus, the need arises to stabilize the voltage gain of each stage. One simple and effective method of stabilize the gain is to use emitter resistance RE as shown in the figure in the CE stage. So, we are adding RE in the previous circuit. The remaining part of the circuits are almost same. Note that in the equivalent circuit, in between collector and emitter, there is a current source HFE-IB. Collector and emitter. Collector and emitter, there is a current source HFE-IB. In this equivalent circuit also, let us show the points emitter, base and collector. This is our base point, this is our collector point, and here it is, say, emitter point. Now we see there is a current source HFE-IB in between collector and emitter. Between collector and emitter, there is a current source HFE IV. So here also there is a current source HFE IV between collector and emitter. But in the previous circuit, there was no resistance between emitter and ground. But here, in this case, there is a resistance between emitter and ground. So, we are putting also a resistance RE between emitter and ground. Again, in the base circuit, input circuit, there is impedance HIE between base and emitter. So here also HIE is the input impedance between base and emitter. So this is the AC equivalent circuit, approximate, simplified, so it is approximated small signal hybrid model is a linear model, so small signal approximation is there. Equivalent circuit, omitting the effect of RB. Note that we have neglected omitting the effect of RB as because base resistance is very high, of the order of megohm. This being in parallel with RB, it can be neglected. 1 by RB plus 1 by R is the effective resistance, so RB can be 1 by RB tends to 0. We can also neglect the effect of CI, input capacitance, and output capacitance. Coupling capacitance are there. These are the coupling capacitance. Also we can neglect CE at mid frequency range. We are considering our frequency is moderate, mid frequency range. If the frequency is large or small, we cannot neglect the effect of junction capacitances as well as there are junction capacitances in between this collector and base. This is a junction between collector and base. There is a capacitance here. There is a junction between base and emitter. There is a capacitance here. All these capacitances are neglected here because we are considering mid frequency for our simplicity of calculation. In my next video on RC coupled amplifier, we will consider frequency responses in the low frequency range as well as in the high frequency range, and in those ranges we cannot neglect these effects of the capacitances. In the mid frequency range, the reactances of the capacitors CI, CO are so small as to constitute a virtual short for the AC components, which I shall discuss in my next video on RC coupled amplifier in very details. The junction capacitances are very small and hence their reactances are very large, as they appear effectively in parallel with the associated resistances. These resistances, junction capacitances, they appears in parallel, so their effect can be neglected. So this is the effectively the approximated small signal equivalent circuit of the CE amplifier with emitter resistance. Now, here is the current IB. So, net current in this branch is IB plus HFE IB. So, net current is IB into 1 plus HFE. IB is from this branch, this is IB, and this branch gives HFE IB. So net current is IB into 1 plus HFE. So what is the current gain now? Current gain is equal to load current divided by input current. Load current is minus HFE IB. Again, load current is in the output direction, and HFE IB which is the true current, which is in the inward direction. So true current IL is equal to minus HFE IB, as it is in the opposite direction. And II is nothing but the base current. Input current is nothing but the base current. So again, the current amplification factor is HFE in the common emitter mode. Now input impedance. This is the current gain. Input impedance, which is input voltage by input current. Input voltage, here it is now HIE IB plus IB into 1 plus HFE into RD. 1 plus HFE IB into RE divided by input current means base current. So it is IB, leaving the net impedance as HIE plus another term which was not in our previous case, in which we have neglected RD. That is, effect of RD is increase of the input impedance by a factor 1 plus HFE into RD. This is the very important effect of the emitter resistance, as because HFE is very greater than HIE. So the total amount 1 plus HFE into RE is very greater than HIE. So input impedance is thus increased by a factor 1 plus HFE into RE, may be very much larger than HIE. The green part is very much larger than HIE. Now voltage gain. Voltage gain is output voltage by input voltage. Output voltage is as usual load current into RL divided by input voltage, input current into input impedance. Again, load current by input current is current gain into RL by input impedance. Putting the values of AI and ZI, we get the net result minus note that AI is equal to minus HFE, so AI is equal to minus HFE into RL, this RL, and ZI is nothing but this HI plus 1 plus HFE into RE. Obviously, the addition of RE reduces the voltage gain, as because denominator increases, voltage gain decreases. But at this cost of reduction of voltage gain, we are getting stabilization, which is more important. The improvement in stability is obtained at the cost of reduction in gain. Now, as this term is very much greater than this term, we can neglect this term. So, it is nearly equal to minus HFE RL divided by 1 plus HFE into RE. And now HFE being very greater than 1, we can neglect this one, so HFE cancels out, and this gives minus RL by RE approximately. So this is the effect of emitter resistance. In a nutshell, RE causes bias stabilization, current gain remains practically unchanged, it increases input impedance by 1 plus HFE into RE, it stabilizes voltage gain. Current gain remains practically unchanged, RE increases stabilization, and input impedance increases by this factor, and it stabilizes voltage gain, as because RL and RE are constant, so it stabilizes voltage gain. So this is the effect of RE, and this shows it is almost stabilized. RL and RE are much more stable than hybrid parameters. Hybrid parameters are very much sensitive to the temperatures, whereas RL and RE are constant. Thanks for watching the video, and if you watch my next video on RC coupled amplifier, it will be helpful for you in understanding why we are neglecting CI, CO, CE here, and if we consider, and we have to consider these capacitances in case of low frequency and high frequency range. Note that we have neglected all this at mid frequency range, that is, frequency used in this signal is not very high or not very small. This is done because, this is assumed because we can neglect the effect of capacitances, external capacitances, CI, CE, etc., as well as the junction capacitances. This is done only for simplification of the calculation and better understanding of the CE amplifier with emitter resistance. Thanking again for watching the video.